Coming to DARPA is like grabbing the nose cone of a rocket and holding on for dear life.
DARPA is a place where if you don't invent the internet, you only get a B.
A DARPA program manager quite literally invents tomorrow.
Coming to work every day and being humbled by that.
DARPA is not one person or one place. It's a collection of people that are excited about moving technology forward.
Hello, and welcome to Voices from DARPA. I'm your host, Tom Shortridge. It's not a secret. The technology that runs modern-day society is vulnerable. Source code, or the set of instructions that tells computers how to perform tasks, is inherently susceptible to cyber attacks for many reasons. But a particular kind of code, called parsers, accounts for nearly 80% of the world's software vulnerabilities. With constant reports of cyber attacks and hacks in the headlines, the prospect of living in a world free of software bugs may seem hopeless. But what if we told you it didn't have to be this way? Here's DARPA Director, Dr. Stephanie Tompkins, on why that is.
Something DARPA invested in over the last decade that we're really proud of and excited by is something called formal methods for software development. And this is this idea that you can actually create software in a way that is mathematically provable, that the software does what it's supposed to do and nothing else. And nothing else is really important because then that essentially blocks hacking.
DARPA experts estimate that if the defense industrial base used formal methods for designing, building, and maintaining software systems, up to 80 to 90% of the Pentagon's cyber vulnerabilities could be eliminated. To break down how, we're joined by Dr. Kathleen Fisher, Director of DARPA's Information Innovation Office. She's a leading formal methods expert who spearheaded some of DARPA's groundbreaking research in the field, including work on the High Assurance Cyber Military Systems, or HACMS, program.
Formal methods is an umbrella term for a range of mathematical approaches to writing software and having it come along with a mathematical guarantee that the software is going to do what it's supposed to do and perhaps more importantly, not do what it's not supposed to do.
In other words, instead of just hoping for the best, formal methods use rigorous mathematical proofs to verify that software behaves exactly as intended.
So formal methods is actually a really old concept. Like from the birth of computer science, when people first started programming computers to do stuff, the idea of let's prove that that code is going to do what it's supposed to has been on the table. For 50 years or more, formal methods researchers have been promising formal methods can do this. But for almost all of that 50 years, it's failed.
So what changed? Why are formal methods suddenly gaining traction after decades of being seen as impractical?
Well, there was a bunch of things that had changed around the time that Hackable started. One was we had had a really long time of Moore's Law improving computers, making computers faster, making more memory available. It turns out that a lot of formal methods is about searching, just exploring a really big space. And the more compute you have, the more memory you have, the more you can search. So just brute force, raw compute power is a significant factor. Another significant factor is better algorithms. And a lot of work had been done in domain-specific languages about can you cast a formal methods problem into a domain-specific language and then generate code to solve the problem. So kind of the machinery of formal methods had advanced significantly right around that time. So there was two pieces of evidence that relevant, interesting pieces of code had been proven to be fully functionally correct.
With more powerful computers and smarter algorithms, formal methods finally became ready for prime time. A novel university experiment that uncovered how vulnerable vehicles were to cyber attacks inspired Kathleen to start DARPA's HACMS program.
So the program was motivated originally by work that showed that you could remotely or wirelessly hack into an automobile and take over control in like 4 or 5 different ways. Modern automobiles are really network computers on wheels, something like 40 to 100 embedded control units, which are just various sizes of computers. They are networked, so they're connected to computers potentially far away, like they have a cell phone, so you can call them from anywhere in the world. And that's just a proxy for lots of other kinds of systems that are also network computers. That was the motivation for, we need to be able to make these kinds of systems more secure. So that's the kind of oh my goodness, this is a surprise moment waiting to happen. We have lots of these kinds of cyber physical systems. They have a computer component, they have a physical component interacting in the world that can be hacked. We need to be able to make these more secure. So that's the problem statement. And then we how can we make these more secure? What's the technology play?
To test her hypothesis that you can use formal methods to retrofit a vehicle and make it provably secure, Kathleen used two systems, an open-source quadcopter and a proprietary Boeing Little Bird helicopter. To establish a baseline, a group of ethical hackers known as a red team was given 6 weeks of full access to both systems to conduct penetration testing. As expected, the red team easily hacked into the quadcopter. More surprisingly, they were also able to wirelessly hack into the Little Bird, much to the astonishment of Boeing's engineers. Kathleen explains what happened next when Hackham's researchers incorporated formal methods.
So baseline, both systems, quadcopter, Boeing, unmanned Little Bird, were susceptible to remote attack. Then the formal methods engineers got to work assessing the software on the system, where it was vulnerable, what they could do to effectively improve the security of the system. They had 16 months to do their work, and then they had to turn it back over to the red team. But the red team wasn't just twiddling their thumbs during the 16 months. They got to watch the entire process. So they knew when they got the system back, they knew everything about the system. They had full knowledge of the system so that when they went to go redo their attack, it wasn't like something that they only had for 6 weeks to understand. They knew as much as possible to know about the system. And so when they came back after 6 weeks of trying to repeat their penetration from the beginning of the program, when they came back after that 6 weeks and could not break into the system, that really said a lot about how secure the system was. That experts who had full knowledge of the system could not break in really showed that the formal methods-based approaches fundamentally changed the security profile of that quadcopter. A colleague of mine who was a program manager at the time, who was an expert in penetration testing, his assessment was that that quadcopter was the most secure UAV on the planet at that time.
DARPA even took the quadcopter to DEF CON and challenged the world's best hackers to try to penetrate the formally verified UAV. They couldn't. But the Hackham's team wasn't done. They still had to prove their methods on the Little Bird. More importantly, the Hackham's team had to teach the Boeing aviation engineers, who were not formal methods experts, to use the mathematical tools and techniques on the Little Bird. Fast forward, after a series of preliminary tests, the outlook for the formally verified helicopter looked promising and had given the Hackham's researchers and Boeing team confidence to do a final test. But this time, the Little Bird would be in flight with 2 test pilots on board.
Basically, we were willing to risk the lives of those 2 pilots because we had so much confidence that the system would work and the helicopter would continue to function as a helicopter, and that the only thing the red team would be able to do was to crash the camera partition. That confidence turned out to be well-placed. The test pilots are fine. So in addition to having increased confidence that the formal methods approaches would work and that the red team would only be able to disrupt their own partition, the camera partition, we also learned that the test pilots couldn't tell that they were flying the high-assurance version. The helicopter was just as responsive as the version without the formal methods-based approaches, demonstrating the effectiveness of the formal methods-based approaches in producing flight-worthy unmanned Little Bird that was also much more resistant to attack from hackers. We started to branch out and apply formal methods-based approaches to lots of other platforms. So by the end of Hackham's, I think there were 10 or 12 other platforms that we'd started to apply formal methods in already.
Since Hackham's, DARPA program managers have been finding new ways to make formal methods easier to use and easier to apply in a lot of other domains. So many that we can't cover them all in this episode, so check out the show notes for more details. But we will highlight a couple, rapid fire, starting with the Assured Micropatching Program, or AMP.
So AMP is about fixing mistakes in programs where you only have the binary. So you have not the source code, just the executable part of the code, but you know that there's a mistake in that code, but for some reason you don't have access to the source code and the vendor is no longer available. Maybe it's in the code that's running in a truck that's deployed overseas. But it has a vulnerability and it's not going to work if you can't get it fixed. But you know what the patch is. You have the source code for the patch. What are you going to do? And it turns out we can solve this problem by taking that binary and decompiling it. Decompiling it is a fancy term for taking the binary, mapping it back to source code. Computers are magic, right? That's something that they can do now. They can take the binary and map it back to source code. Turns out there's more than one way you can do that. And what we can do is we can guide that decompilation process back in a way that matches the patch that we have, which sounds like magic, but has actually been proven to work in the AMP program. We've done that actually on trucks and the code that runs like engine controllers. And we're working on doing it right now on satellites, which are systems where, they deployed up in space and you can't actually get access to it anymore.
Speaking of magic, the VSpells program, short for Verified Security and Performance Enhancement of Large Legacy Software, is helping developers improve software architecture and design by automatically analyzing legacy software, with or without its source code, and using that analysis to aid in modernization.
You have existing code that you need to upgrade, but maybe wasn't designed using the cleanest software engineering practices. So instead of being beautifully modular where you can go find, here's this component that you want to upgrade, it's all kind of spaghetti code and spread out. And one of the canonical examples of this is the parsing code is spaghettied throughout a whole bunch of the system. Like somebody wrote by hand the parser, already something we don't really like, and the code for processing the data that's been parsed is integrated in along with the parser. And we want to replace that handwritten parser with a formally verified generated parser. But we have to do the detangling. That's what the VSpells program is all about. Not for parsers particularly, but for lots of examples like this where we want to upgrade a part of the system, but we first need to detangle the spaghetti code, identify the part of the system that we want to be able to upgrade, lift it out, revise that part of the code, and then recompile it back into the whole system. And so that also sounds like magic, but has been using the power of abstraction and domain-specific languages to identify the sort of logical modules that are in the spaghetti code, lift them out, replace those pieces, and then recompile it.
Proving that formal methods are ready for prime time is one thing. Actually transitioning these tools to the various services within the DoD is a whole different story. DARPA is working with a variety of partners representing the various military branches who can help connect science and technology innovations from the lab to the real world. One of these partners is Felix Cortez, a technical leader within the Software Directorate working with the 76 Software Engineering Group and a bridge builder between the labs and operational communities. His group supports Air Force and Department of Defense working groups dedicated to rapidly transitioning cutting-edge research into warfighter capabilities. His work with the VSpells program is paving the way for how to adopt formal methods techniques.
We started with the VSpells program very early on, and we saw a lot of hope and a lot of ideas of where we could take VSpells. The idea that we had early on was we have this repository of legacy code, and if we could take that code base and generate smaller modular models from that legacy code base, you start to look at this repository more like an app store that we can leverage our legacy avionics software investment for new platforms and not worry about, say, hardware dependencies or other things that kind of hindered us in the past that models kind of bring to the table. And so specifically within the VSpell, we can focus on these models to make sure they're comparable by construction to ensure that the model that's generated is correct from the start. And that's called correct by construction. And so we call this kind of the lift and shift strategy, where we can maximize reuse. That idea, that concept was really exciting for us, which is why we've gone through the various stages with DARPA to where we're at now, where we're ready to show a demonstratable product and then hopefully take that product and transition it as part of a capstone within a larger effort. In terms of what our transition partners, what our program offices would need, and help transition that technology and just say, hey, how would this benefit you? How refactoring the models will help you in certain things like providing artifacts for airworthiness or supporting a hardware refresh where you don't really have to focus on specific hardware requirements or dependencies or APIs, right? And so that's our role. We take that tool set that DARPA provides and we implement that tool and demonstrate capability on a real program or project.
With the latest advances made possible by large language models like ChatGPT, formal methods' potential to scale has reached new heights. Brad Martin is an expert in formal methods with more than 30 years in this field under his belt. His tour as a program manager at DARPA ended in the summer of 2024. While he was here, Brad launched and executed programs aimed at increasing the usability and scalability of formal methods, many of which are in use by various parts of the government. Here's Brad on the concept behind the Pipelined Reasoning of Verifiers Enabling Robust Systems, or PROVERS, program.
We're really at a tipping point for formal methods in regard to the infrastructure that we've been developing for decades around specific formal methods tools that are really coming into their own. Opportunities for their use to advance the scope, but also in some sense almost a desperate need for capabilities to be able to say something strongly about our software and systems from a security and a safety perspective. The lift of formal methods tools, which can be hard if you don't have a PhD in that space or maybe you hadn't built the tool yourself. So really wanted to push on the usability of those tools, the scalability of those tools to see, again, more traditional developers being able to use those tools to scale. My goal there was still with this view of wanting to push on automation and usability and scalability. I wanted to see how impactful could AI and machine learning be in the synthesis of proofs as well as the repair of proofs. One aspect of that we'd seen from big tech companies like AWS and we'd seen from Facebook, now Meta, was about driving the tools into the workflows of developers of your systems. And so not only pushing on the capabilities for those tools to be used in an automated way and extend the reach of those tools, but also to drive them into the workflows so they would meet the developer where they were. So that was one key aspect of that program. Other aspects are about leveraging those tools in concert with platforms of interest from a national security perspective.
By making formal methods accessible to non-experts, the ability to extend their use appears to finally be within reach. DARPA and other experts say the time is now to show the art of the possible to those who stand to benefit from these tools. Here's Brad again.
It's just now a matter for the defense industrial base. How do we get these tools in the hands of the developers that are building our systems and leverage them in a way that they can actually be used by developers, engineers, designers of our systems within the defense industrial base? So it's probably not even a year into provers yet. The great thing about DARPA is its willingness to take risks. And so to push on very challenging problems and to understand that some of those will be successful, some of them won't. And so we're yet to see the results. Although I think we've seen some early examples of work coming out of that. It's yet to see if we'll be able to realize the goals of provers. But I'm hopeful. And I think, again, the time is just right for maybe we'll be able to achieve those strongest challenges, but at least I believe we'll be able to have impacts that will really provide dividends for the DoD.
Like a typical DARPA hard problem, the technical transition of these tools is just as difficult, but not impossible, according to Dr. Benjamin Bishop, who goes by the call sign Bach. Remember that stat about eliminating up to 90% of the DoD's software vulnerabilities with formal methods? As DARPA's Deputy Director of the Adaptive Capabilities Office, Bach is focused on helping the DoD widely adopt these tools and turning that vision into real-world impact.
Sometimes achieving a successful technology may be the easy part of it. When DARPA finishes a research and development program, where does that technology go? How does it continue? Where our team in the Adaptive Capability Office focuses on is how do we realize the impact of the technology and how do we help program managers realize their vision to go change the world? So what we help program managers with is understanding how the DoD works, how the warfighter works. We work hand in hand with our service liaison officers that are also stationed here at DARPA and help connect the program managers with the user, but also with the people that work within the Pentagon that determine what are the military requirements. How do we resource and spend money on future technologies? And then helping the program managers take their successful technology and get it into the hands of the warfighters because it has to navigate that system. Or perhaps maybe we help them get it into a new technology standard that is widely adopted, which again is what we're trying to do with the Resilient Software Systems portfolio.
So, transitioning technology isn't simply handing it off, but requires a thoughtful approach to implementation.
As I look back and reflect on how the Resilient Software System portfolio has progressed, it started with a lot of successes across the Department of Defense, individual DARPA programs, meeting their technical metrics, showing that this technology approach works, and then actually having a transition partner adopt it. But it was very distributed, and Dr. Tompkins saw the potential of the Resilient Software Systems portfolio and the promise of formal methods and applying it at scale. And she asked Dr. Fisher and myself to come up with a plan to transition it at a much larger scale. What we came up with is the idea of taking, a bunch of different formal methods applications and a bunch of different programs within the resilient software portfolio and actually trying to go do it at scale with a partner, specifically with a service partner. And instead of just doing it in individual aspects, do it with the entire systems office. Manage a major weapon system and then implement these techniques throughout it and get an early adopter and early adoption.
It sounds like you were working to create a cultural shift in how software is developed and implemented within these organizations. With these large-scale transitions, how do you ensure that the impact of these technologies is fully realized?
So I'm excited to report that we're having active conversations with the services on a daily basis about what programs might really benefit from this. And then where should we focus first and go demonstrate the success? And really, as you look at change management, how do you get your early adopters? And you show success there and then you scale. So I'm really excited about these conversations that we're having with the services and then also with the Office of Secretary of Defense for Acquisition Sustainment and using their position within the Department of Defense to help articulate best practices guides. So as we do these capstone exercises, we're actually documenting the learning and we're able to share it across the Department of Defense.
Changing a paradigm is never an easy feat, but it is possible. It starts with early adopters and requires a deep understanding of the environment you seek to change. In the case of revolutionizing cyber resiliency for the U.S. military using formal methods, it boils down to burning down risk and knowing how to insert new technology. And in the U.S. military, it's about working with the service's program management offices. In other words, dedicated units responsible for overseeing and managing the execution of specific defense programs or projects. Here's Felix again to explain.
Program offices have very specific directed money to do, XYZ. And there's risk in doing something new because we know how to accomplish XYZ through traditional means. So you're not going to see a requirement to say, use this new technology to accomplish XYZ. It's just accomplish XYZ. But they want to use new technologies, and there's an appetite to transition and move faster and do things a new way. Having something in between and saying, what have we already looked at and investigated and had some way of shaping it early on to say, look, we've been maturing, in this case, these spells from inception, from phase 1 to phase 2 to phase 3, and now we're looking at a capstone. We started this maturation process all the way through to de-risk that technology to be prepared for a transition effort. Now, there still might be some effort to be done after that, but the idea here is to reduce the risk of transition for a program office because each individual program office has their own risk tolerance. And what I would say is once you do a particular program office, the burden gets reduced for another program office. And then once you do 2, the burden continues to go down to 3 and then down to 4 until it becomes standard operating procedure to use that technology for that particular use case. We wouldn't know that unless we understood how both entities operate. And then once you understand that, then you can help align each other's missions. That's where the magic happens, because I think the ultimate goal is the same. How do we help the warfighter?
Rapid action to implement these tools in legacy and future systems can dramatically reduce U.S. software vulnerabilities ahead of future global conflicts. Given the current threat landscape, we can no longer afford the status quo approach to cybersecurity. Here's Kathleen.
So the OD&I assessment that comes out every year has highlighted that the U.S. has a significant technical debt with respect to our critical infrastructure and the software in our critical infrastructure. We saw with the Volt Typhoon reporting and what Microsoft is reporting that China has put implants in our critical infrastructure, both civilian and military, so that they have the capability of carrying out such attacks. The goal here is to change the mindset from business as usual, which is the current state, into a new mindset where we can produce systems that are dramatically harder to hack into. DARPA has already shown that it is possible to produce software that has that much higher standard of correctness, much, much harder to hack into. What we currently lack is the will to do that. And hopefully we shift into the mindset of we can do this before we suffer the consequences of not having done that already.
That's all for this episode of Voices from DARPA. Thank you for joining us on this exploration of formal methods and their potential to safeguard our digital world. Check out the show notes for additional resources to learn more about the projects our experts discussed and more. Thanks to Heather Dees for producing this episode. And thank you for listening.